Hello. Mic texting. Hello. Mic testing. One, two, three. Hello.
नमस्कार साथियों, एक बार फिर से स्वागत है आपका। हम फिर फिजिक्स के बाद अब क्लास का केमिस्ट्री का फर्स्ट चैप्टर लेके आए हैं। फर्स्ट क्लास क्लास 12th की फर्स्ट चैप्टर जो कि सॉलिड स्टेट है। अगर आपने फिजिक्स का क्लास नहीं देखा है तो जस्ट अभी फिजिक्स का क्लास हुआ है, इसके बाद देख लीजिएगा, ठीक है। भाई अगर नए आए हैं तो लाइक कर दीजिए। अभी आप आए हैं स्ट्रीम में तो लाइव को लाइक कर दीजिए, कमेंट कर दीजिएगा और शेयर करना ना भूलिएगा। थैंक यू। चैप्टर 1 का नाम है द सॉलिड स्टेट। शुरू करते हैं हम इस चैप्टर को। दोनों बाइलिंगुअल रहेगा, हिंदी में भी समझाएंगे, इंग्लिश में भी समझाएंगे।
In this module, we will be studying about the general characteristics of solids. As you know, based on the forces of attraction between the constituent particles such as atoms, ions, or molecules, the matter exists in three different physical states, namely gaseous state, liquid state, and solid state. You know that the constituent particles in gases and liquids are held together by relatively weak forces of attraction as compared to those in solids. As a consequence, they can translate randomly, rotate, and vibrate. Gases and liquids thus have the ability to flow and take shape of their container. On the other hand, the constituent particles in solids are held together by strong forces of attraction. In other words, the constituent particles are closely packed. However, these particles can still vibrate about their fixed mean positions. Solids possess some characteristic properties attributed to their closed packing. They have a definite shape and volume, lack the ability to flow, and are incompressible and rigid. In general, the distinct properties of the three different states can be attributed to the arrangement of the constituent particles. In other words, any change in the arrangement of these constituent particles changes the physical state of a substance. In turn, the arrangement of the constituent particles in a particular substance depends upon the external conditions of temperature and pressure. For example, at 1 atmospheric pressure, water in the liquid state gets converted into its solid form, ice, at 0 degrees Celsius or 273 Kelvin. Let us explore how the molecules of water in liquid state attain the molecular arrangement of water in solid state. On cooling, the potential energy of the liquid molecules is released in the form of thermal energy. As a consequence, the space between the molecules decreases and the intermolecular forces of attraction increase. Also, the molecules lose their translator movement and rotatory movement, and they can only oscillate about their fixed mean positions. Thus, the molecules of the liquid attain the molecular arrangement of the solid. Let us now explore how the structure and properties of a solid are correlated to one another. The nature of the constituent particles, the forces of attraction between them, and their arrangement together determine the structure of a particular substance. The properties of any solid substance ultimately depend on its structure. Hence, any change in the structure of a substance changes its properties. For example, the conductivity of silicon increases with the addition of impurities such as arsenic. So, a solid with the desired properties can be prepared by altering its structure. Some solid materials that were prepared for applications in various fields are superconductors, certain ceramics, synthetic biopolymers, and carbon nanotubes. In this module, we will be studying about crystalline and amorphous solids. On the basis of the arrangement of its constituents, solids are broadly classified into two categories. They are crystalline solids and amorphous solids. Crystalline solids have an orderly arrangement of their constituent particles, such as atoms, ions, or molecules in 3 dimensions. They are arranged in an orderly manner to give a definite geometry to the crystal. Thus, a crystal is defined as a solid figure that has a definite geometrical shape with flat faces and sharp edges. Quartz and sodium chloride are examples of crystalline solids. Let us now study about amorphous solids. The term amorphous has been derived from a Greek word, amorph, which means shapeless. An amorphous solid consists of a number of constituent particles arranged in a random manner. Thus, amorphous solids do not have any definite geometry. There is a short-range order, which means that there is an irregular arrangement of particles that repeats itself to a certain extent only. Glass, rubber, and plastics are examples of amorphous solids. In many respects, these solids resemble liquids. They flow very slowly at room temperature and are regarded as supercooled liquids, in which the forces holding the molecules together are so great that the material is rigid, but there is no regularity in the structure. The flow of these solids is clearly observed in glass panes fixed to the windows or doors of old buildings. These are found to be slightly thicker at the bottom than at the top. Here you can see the arrangement of a quartz, which is a crystalline solid, and also of quartz glass, which is an amorphous solid. From these two images, you can clearly observe that both solids have similar arrangements. However, in quartz glass, there is short-range order. A crystalline solid has a sharp melting point. That is, when it reaches its melting point, it immediately changes into liquid form. These are considered true solids. Amorphous solids do not have sharp melting points. These soften over a range of temperatures and can be molded and blown into various shapes. These solids behave as crystalline at a certain temperature. These are considered pseudo-solids or supercooled liquids. Crystalline solids are anisotropic in nature. In other words, some physical properties like refractive index and electrical resistance change along with the change in the direction of the solid. This is due to the ordered molecular arrangement in the solid. Amorphous solids are isotropic in nature. In other words, they show the same physical properties in all directions. This is due to the random arrangement of the solid. If a crystalline solid is broken into pieces, the small constituents will have the same smooth and plane surfaces. However, if amorphous solid is broken into pieces, the small constituents will have irregular surfaces. Crystalline solids have the definite heat of fusion values, while amorphous solids do not. Another important property of these solids is symmetry. Crystalline solids show plane of symmetry, axis of symmetry, and center of symmetry. On the other hand, amorphous solids do not show any symmetry. Let us now study about metallic and covalent solids. Let us begin our discussion with metallic solids. In metallic solids, the metal atoms such as copper, iron, silver, and magnesium lose their valence electrons to the crystal as a whole. These solids are merely a collection of positive ions surrounded by and held together by a sea of electrons. Hence, the constituent particles in a metallic solid are positive ions in a sea of delocalized electrons. The electrostatic forces of attraction between the positive ions and the electron cloud constitute the metallic bonding, which holds the positive ions together. These electrons are not localized on any atom, but rather delocalized uniformly over the entire crystal. These free and mobile electrons make metallic solids good conductors of electricity and heat. The electrons flow through a network of positive ions when an electric field is applied. Similarly, when heat is applied to one corner of a metallic solid, the free electrons spread the thermal energy evenly throughout the solid. The presence of free electrons also accounts for the luster and color in some cases. Metals are highly malleable and ductile. Metallic solids have fairly high melting and boiling points. Let us now study about the other type of crystalline solids, that is, covalent or network solids. The constituent particles in these solids are atoms. These atoms are held together in large networks by covalent bonds. This interlocking network of covalent bonds extends throughout the crystal in all directions. Hence, covalent solids are also called network solids. They are also termed as giant molecules. Diamond, graphite, and quartz are some network solids. As the atoms are held by strong covalent bonds, these solids are very hard and possess very high melting points. These solids are non-conductors of electricity except for graphite. In diamond, each carbon atom is bonded tetrahedrally to 4 other carbon atoms. Thus, a regular tetrahedral arrangement of carbon atoms bonded to one another in a 3-dimensional manner forms a network, resulting in a rigid giant molecule. It is important to note that diamond is the hardest substance known and has a melting point of 3550 degrees Celsius. On the other hand, graphite is an exceptionally good conductor of electricity and is extremely soft. In graphite, each carbon atom is bonded to 3 other carbon atoms, resulting in hexagonal rings, which when repeated throughout a plane, form sheets or layers. In its layered structure, the layers of hexagonal rings are arranged parallel to each other, as shown here. These layers are held together by weak van der Waals forces of attraction. The layers can slide over one another when impurities are present between them. On account of this, graphite is soft and can be used as a solid lubricant. As each carbon atom in graphite is bonded to only 3 other neighboring carbon atoms, the 4th valence electron is free to move about in different layers. Thus, the free mobile electrons account for the exceptional electrical conductivity in graphite. In this module, we will be studying about crystalline lattice and unit cells. Crystalline solids have an orderly arrangement of their constituent particles in 3 dimensions. The positions of these particles in a crystal related to one another are usually shown by points. An arrangement of an infinite set of these points is called a crystal lattice. Thus, the crystal lattice is a regular arrangement of the constituent atoms, ions, or molecules in 3-dimensional space. Sometimes, a crystal lattice is also called as space lattice or simply a lattice. There are only 14 possible 3-dimensional lattices and are called Bravais lattices after Auguste Bravais, a French mathematician, who first described them. Now, let us look at the characteristics of a crystal lattice. Each point in a lattice is called a lattice point or lattice site. Each point in a crystal lattice represents one constituent particle, which may be an atom or molecule or an ion. Lattice points are joined by straight lines to bring out the geometry of the lattice. A crystal lattice can be subdivided into several cells, known as unit cells. Thus, a unit cell can be defined as the smallest portion of a crystal lattice, which, when repeated in different directions, generates the entire lattice. A unit cell represents the shape of the entire crystal. In fact, a crystal may consist of an infinite number of unit cells. A unit cell is characterized by distances A, B, and C along three edges, and angles alpha, beta, and gamma between pairs of edges. Alpha is an angle between edges B and C. Beta is the angle between edges C and A, while gamma is the angle between edges A and B, as shown here. An important point to note is that edges A, B, and C may or may not be perpendicular to each other. Let us now study about the types of unit cells. Unit cells can be broadly classified into two categories: primitive unit cells and centered unit cells. Unit cells in which all the constituent particles, such as atoms, ions, or molecules, are present only at the corners, are called primitive unit cells. Unit cells in which one or more constituent particles are present at positions other than its corners, in addition to those at the corners, it is called a centered unit cell. Based on the position of the centered constituent particle, centered unit cells are characterized into three types: body-centered unit cell, face-centered unit cell, and end-centered unit cell. A body-centered unit cell has constituent particles at all its corners, as well as one particle at its body center, as shown here. A face-centered unit cell has constituent particles at all its corners, as well as at the center of each face. An end-centered unit cell has one constituent particle at the center of any two opposite faces, besides the ones present at its corners. You know that a three-dimensional crystal lattice is generated by the translation of lattice parameters A, B, and C. Based on lattice parameters, we have 7 popular crystal systems, namely cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and triclinic. In this module, let us further study about the unit cells. You already know that every crystal lattice is made up of an infinite number of unit cells, and every lattice site is occupied by a constituent particle. That may be an atom, an ion, or a molecule. Now, let's examine what portion of each particle belongs to a particular unit cell. Consider three types of cubic unit cells. For the sake of simplicity, assume that the constituent particle is an atom. Let's start with a simple or primitive cubic lattice. A simple cubic lattice consists of 8 atoms at the 8 corners of a cube. In the open structure shown here, the distances between the atoms have been exaggerated. In reality, the atoms are packed much more closely together, as shown in the space-filling model here. The space-filling model shows that the atoms touch along the edges of the cell. By considering the portion of atoms inside the cell boundary, we can generate a unit cell of a simple cubic lattice. From this, it is evident that each atom at the corners contributes 1/8 of its original volume to each unit cell. There are 8 atoms at the 8 corners. Thus, the number of atoms in each unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. A body-centered unit cell contains 8 corner atoms, just like in a simple cubic unit cell. However, there is one more atom at its body center. As a result, the atoms at the corner no longer touch along the edges of the cell in the space-filling model. The unit cell of a body-centered cubic cell is shown here. It is clear that the 8 atoms at the corners contribute 1/8 of their actual volume each. In addition, one atom lies completely inside the cell. Therefore, the number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. There is one atom at the center of the cube. Thus, the total number of atoms in a body-centered cubic unit cell is 2. The face-centered cubic lattice consists of 8 corner atoms, just like in the simple and body-centered cubic lattice. However, it also contains 6 more atoms at the 6 faces of the cube cell. The atoms touch along the diagonals and each touches 4 corner atoms. A unit cell of a face-centered cubic cell is shown here. clear that the atoms at the corners contribute 1/8 of their original volume each. The number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. The number of atoms present at the faces per unit cell is equal to 6 atoms at the faces into half an atom per unit cell, which is equal to 3. Thus, the total number of atoms per face-centered cubic unit cell is 4. In this module, we will be studying about the close-packed structures. When substances form solids, they tend to pack together to form ordered arrays of atoms, ions, or molecules. Let's see how this order arises and what different kinds of arrangements are possible. A honeycomb is an excellent example of close packing found in nature. A close packing is thus defined as a way of arranging equidimensional objects in space such that the available spaces fill very efficiently. Solids are three-dimensional objects, and we will develop their structure in 3 steps. To understand how the constituent particles are packed, let us assume that these particles are hard spheres of identical size. First, let's look at closing packing in 1 dimension. You can see that there is only one way of arranging the spheres in a 1-dimensional close-packed structure, that is, by arranging them in a row touching each other. In this arrangement, each sphere touches 2 neighboring spheres. In general, the number of nearest neighbors of a particle is defined as its coordination number. Therefore, the coordination number of a particle or sphere in 1-dimensional close packing is 2. Let's now look at close packing in 2 dimensions. When n number of rows are stacked up, a 2-dimensional crystal plane is generated. Obviously, there are 2 ways of stacking the rows. One way is for the rows to lie above the other, with one sphere exactly above another. You can see that the spheres are aligned horizontally as well as vertically. If the arrangement of the spheres in the first row is said to be of A type, then the arrangement of the spheres in the successive rows is also of A type. The packing thus obtained is called AAA type packing. You can also see that each sphere is in contact with 4 other spheres, 2 on either side, 1 above and 1 below. Hence, the coordination number becomes 4. Also, if you join the centers of these 4 spheres, you will get a square. Therefore, this type of close packing is also referred to as square close packing. The other way is for the spheres of the second row to be seated on the first row in a staggered manner, that is, in the depressions of the first layer. The spheres of the third layer are placed in the depressions of the second layer, and so on. Evidently, The spheres in the third row are vertically aligned with the spheres in the first row. This pattern is followed throughout. If the arrangement of the spheres in the first layer is of A type, then the arrangement of the spheres in the second layer is of B type. And the arrangement of the spheres in the third layer is again of A type. And so on. The packing thus obtained is called AB-AB type packing. You can also see that each sphere is in contact with 6 other spheres, 2 on either side, 2 in the layer below, and 2 more in the layer above. Hence, the coordination number of a sphere becomes 6. Also, if you join the centers of these 6 spheres, you get a hexagonal pattern. Therefore, this type of close packing is also referred to as hexagonal close packing. If you compare the two arrangements, you can see that in hexagonal close packing, the constituent spheres occupy the space more efficiently. Therefore, constituent particles will arrange themselves in hexagonal close packing in a plane or 2 dimensions. Some spaces are left vacant after the close packing of the spheres. These vacant spaces are called voids or interstitial sites. In the figure, the empty spaces are seen as curved triangular spaces. These spaces left between the spheres can be divided into 2 kinds, B and C. The spaces marked B are the ones in which the apex of the triangular spaces is pointing downwards, while the spaces marked C are the ones in which the apex of the triangular spaces is pointing upwards. As real crystals are all 3-dimensional in nature, we will use this 2-dimensional hexagonal close packing to build through 3-dimensional structures later on in this course.
सो ये थी आपकी केमिस्ट्री की क्लास 12th की फर्स्ट चैप्टर की क्लास, ठीक है। फिजिक्स की हुई थी, इसके बाद ये केमिस्ट्री की थी। अब इसके बाद होगी मैथ्स, तो बने रहिएगा। आई होप कि आपने सेशन को जरूर लाइक किया होगा, कमेंट भी किए होंगे, और अच्छा लगा तो आपने शेयर तो किया ही होगा, है ना। तो बने रहिए, अगले 5 मिनट में अब आपकी क्लास 12 की मैथ्स की चैप्टर फर्स्ट की क्लास होने जा रही है, ठीक है। So thank you so much for being with us.